We're going to look at improper integrals in this particular video. In order to motivate them, I want to look at a couple of proper, I guess you would call them, integrals, ones that we're familiar with already. Let's take a look at the integral from 1 to 10 of 1 over x squared. Well, that's x to the negative 2. You find the antiderivative, which is negative x to the negative 1. When we substitute 10 and 1 in, we get negative 1/10, essentially plus 1, right? Minus negative 1, which is 9/10. Let's expand this interval from 1 to 10. Instead of going from 1 to 10, we'll go from 1 to 100. When we do that, we end up with the same antiderivative, but now we're going to substitute 101 in instead, and we end up with essentially 1 minus 1/100th, which becomes 99/100ths. Well, let's go for the gold, and let's go all the way out to 1 million. When we go out to 1 million, we have the same antiderivative. I didn't write it in this step, but we do. We evaluate it at 1 million and at 1. Here's the 1. And here's the evaluation at 1 million, which is 1/1,000,000th. And so we end up with 999,999 millionths. And as we can see, as we continue to let this upper limit grow and grow and grow, this is going to approach 1. It's pretty easy to see why that's going to be. And so we're going to write this. We're going to have to make a new definition for an integral, which we'll do in a couple of minutes here. But we're going to write the integral from 1 to infinity of 1 over x squared is equal to 1. Well, now let's change 1 over x squared to something that seems very much related. Let's change it to 1 over radical x. I'm choosing my upper limits so that they evaluate nicely. 1 over x, remember, is the same as x to the negative 1/2. If we add 1 to the exponent, we get 1/2. When you divide by 1/2, it's like multiplying by 2, and so that's where this extra 2 comes from in the front of the square root sign. We've added 1/2 to the negative 1/2 to get positive 1/2. When we evaluate this at 9 and 1, we end up with 2 times 3. 2 times 3 is 6. 6 minus 2 is 4. Now let's change it to another limit. Instead of going to 9, let's go to 100. 1 over x radical x, same antiderivative. We evaluate it at 100. 2 times 100 is 20, minus 2 is 18. And then when we do it from 1 to 1 million, we end up with 2 times radical 1 million, which is 1,000. 2 times 1,000 is 2,000, minus 2 is 1998. And so you can see that these numbers here are not approaching a single number like they were before. Instead, they're getting larger and larger and larger. And by choosing the upper limit to be even larger, this will go on to be any large number that we want. And so we're going to say that this integral diverges. We're going to use some different language here. We're going to use diverge when something like this happens. We go off to infinity. There are other circumstances where we would say it diverges, but that's one of them. We're going to say it converges like it did in the previous example. So this is the way that we defined the definite integral. We had to have one special stipulation in our theorem that f is a continuous function, which is okay. We're good with that in our particular functions. F is continuous, and when that happens, we have this summation that is the definition for this definite integral, but it has to be on a finite interval from a to b. In that light, this is nonsensical. It has no meaning. And so what we do is we define the integral from a to infinity to mean the limit as b goes to infinity, integral from a to b, f of x dx. So we will always rewrite it like that. It is incorrect to do it any other way. Well, one type of improper integral will kind of jump out and say, hey, I'm improper, and that's one where the upper limit is infinity, or maybe the lower limit is negative infinity, and we can even see ones where we have both negative infinity and positive infinity. So that's one way we can have an improper integral. We're going to have two different types of improper integrals. The first we've already seen, which are the ones where either the upper limit or the lower limit tends to infinity, or negative infinity if it were the lower limit. The other type refers to one that we dealt with earlier, where I mentioned something about the function being continuous. Well, suppose we have an integral from a to b, and the function is discontinuous at b. That violates the definition that we made of the definite integral. And so what we can do is we can let t approach b. We would do it from the left. Let me draw a little interval here. If you think about the interval going from a to b, what we're going to do is we're going to take the integral from a to some number t and then approach b from the left. We'll look at the integral from a to t then instead and see what happens to that integral. If the limit exists, we say the integral converges. Otherwise, we're going to say that the integral diverges. Let's look at our first example, which is one of these type 1 improper integrals. So we have the integral from 1 to infinity of e to the negative 0.15 t. Now, we might be able to get away without this, but I'm going to make a substitution here. But before we do that, let's go ahead and acknowledge the fact that we are dealing with an improper integral. We need to write this as the limit as b goes to infinity, the integral from 1 to b, e to the negative 0.15 t dt. Okay? Otherwise, it's nonsense. We can't substitute infinity, and that's nonsensical. So what we'll do in this case is we can let u be equal to that negative 0.15 t, the exponent. You might be able to get away without it. I'll hint as to how you do that once we get through all this. Then du is going to be negative 0.15 dt. And we don't have a negative 0.15 lurking about, so we'll divide by negative 0.15 on both sides. Negative 1 over 0.15 du is equal to dt. So we go ahead and we do this. We say that's equal to the limit as b goes to infinity. We'll pull the negative 1 over 0.15 out in the front. And then our integral is going to go from 1 to b, e to the u du. Now sometimes we like to change those limits of integration, and you're more than welcome to do that. When I'm doing improper integrals, I feel a little better about going ahead and doing the substitution and then resubstituting afterwards. So, well, the integral of e to the u is exactly e to the u. That's kind of nice. So we have the limit as b goes to infinity, negative 1 over 0.15 e to the u. Now remember, this is going from t equals 1 to t equals b, so we have to resubstitute. This is the limit as b goes to infinity of negative 1 over 0.15 e to the negative 0.15 t, evaluated from t equals 1 to t equals b. Now we'll substitute. We have the limit as b goes to infinity, negative 1 over 0.15 e to the negative 0.15 b, when t is equal to b, we get that. And then we're going to subtract this all, but because I'm subtracting a negative, I'm really adding 1 over 0.15 e to the negative 0.15 times the lower limit, which is 1. Now this is the limit of all this stuff, but the only place where we see a b is in that very first term. Okay, so I want to think about what happens when b is a very, very large number. If b is a very, very large number, then the exponent is, well, it's a negative number multiplied by a very, very large number. So I'm going to say this is kind of strangely, but it's a huge negative number. It's a negative number that when you take its absolute value is very, very large. And so I think to myself, well, what is a e to a huge negative number? Well, okay, maybe I don't know. And so I say, well, what does that negative exponent mean? Well, a way to interpret negative exponents is to write it as 1 over e to that huge number. Now, I'm a big fan of exponential growth. That's the way my bank grows, not very quickly, my bank account. When I have e to a huge positive number, I end up with quite something quite large. I'm going to say it's huger. I know it's not a word. But if you divide 1 divided by some ginormous number, it's going to be essentially 0. So that first term is going to tend towards 0, and the second term will just be 1 over 0.15 e to the negative 0.15, or if you want to be super fancy about it, you can say it's 1 over 0.15 e to the 0.15. Now I've run out of room, but I want to demonstrate exactly what's happening here. So before I do that, we're going to say that this integral converges. Because I ended up with a numerical answer for this, we'll say it converges. Okay, back to my extra little bonus here. I'm trying to understand exactly what I've just done. Remember that one application of integrals is that they measure area bounded by the curve in the x-axis. So a rather imprecise drawing here, but this exponential function looks something like this overall. If I start at x equals 1 or t equals 1, what I'm trying to do is I'm trying to measure the area bounded by the curve and the x-axis. And so what this is saying is that the area is finite. Not only is it finite, it's 1 over 0.15 times e to the 0.15. So not a very big number overall. Okay, for our next example, let's look at this one. We have, again, one of these, we called it a type 1, where the top limit is going to infinity. Another type 1 type is when the bottom limit goes to negative infinity, but that's what we have here. Okay, so I have to figure out, well, wait, before I do that, let's do this. We want to write it as the limit as b goes to infinity, integral from 0 to b of x plus 1 over x squared plus 2x plus 3 dx. Okay, so now I have to figure out a way to evaluate this integral. Well, it looks like a partial fractions problem. It really does. Before I try any partial fractions problem, I actually cast a suspicious eye and say, wait a minute, maybe substitution is more appropriate here. Let's think about what would happen if I let u be the denominator. The derivative of the denominator would be 2x plus 2. 2x plus 2, when you factor out the 2, you'll get x plus 1. So this is more appropriate to use substitution for this problem than it is to use integration by partial fractions. Okay? Even partial fractions would be tricky because that denominator, in fact, does not factor. So, okay, so let's do that substitution. We'll let u be equal to x squared plus 2x plus 3. So du is 2x plus 2, all of that multiplied by dx. And as I said, there's a factor of 2 that we could pull out. Du will be 2 times the quantity x plus 1 dx. If we multiply both sides by 1/2, we get 1/2 du is 2 times the quantity of x plus 1 dx. Okay, so we're going to go ahead and make this substitution. Let's see here. So this will become the limit as b goes to infinity. We're going to go from 0 to b. Ooh, I didn't do this. Oops, and there's a mistake over here. We should not have this 2 in front of the x plus 1. It should just be x plus 1 there. Okay, so I noticed that because I was thinking that I forgot to pull the 1/2 out front. Okay, so I'm sorry for doing that. But x dx is 1/2 du, which I'm going to put the du in the numerator. The denominator becomes just u. And now this is a nice antiderivative. We recognize this. It is the natural log. And I'm going to go ahead and say, well, I should be careful here. Let me put the absolute values on. I'll explain why I need to be careful. This is going to be 1/2 natural log of the absolute value of u. Make that look more like a u. We want to evaluate this not from u equals 0 to b, but from x equals 0 to b. So I'm going to substitute the x squared plus 2x plus 3 in. Now, I mentioned earlier that that doesn't factor. The reason that doesn't factor is because if you were to graph that, or one justification for why it doesn't factor, if you were to graph that function, it would be a parabola that opens upward that lies entirely above the x-axis. In order to factor, it would have to cross the x-axis. So this is always a positive value. So now I am going to drop those limits there, or the absolute values. We're going to have 1/2 natural log of x squared plus 2x plus 3 evaluated from 0 to b. When x is equal to b, we're going to get, let's see, the limit is x as b goes to infinity, 1/2 the natural log of b squared plus 2b plus 3 minus 1/2 the natural log, and I'm going to go ahead and just shortcut this. When x is equal to 0, we'll have 0 squared plus 2 times 0 plus 3, which is just 3. All right, so now we have to evaluate the limit, and this is where things get a little bit tricky. The natural log of b squared plus 2b plus 3. Again, don't try to do it all at once. Just think about what's happening here. In this b squared plus 2b plus 3, the most influential term there is the b squared. Okay? When b is really large, 2b is going to be very, very small in comparison to b squared. So when b is very large, b squared is larger. When you take the natural log of a number that keeps getting larger and larger and larger, the natural log is also going to get larger and larger and larger. And in fact, it knows no bound. It will get as large as we want. So this first term is going to approach infinity. And so we'll say the whole thing approaches infinity. So this particular guy diverges. It's sad. It diverges. Okay, so overall, here's something that we should know. When an integral approaches infinity like this, that's a case that it would be, as we say, a divergent series. For our next one, we once again have one of these type 1 improper integrals where the limit approaches infinity, or the upper limit approaches infinity. Once again, we'll do as we did before. We really need to do this every time. It's the limit as b goes to infinity of the integral from the natural log of 4, that's a strange limit, to infinity, oops, not to infinity, that's what I'm doing this for, from natural log of 4 to b, of x e to the negative x dx. Okay, this is going to require some of our integration techniques. In the previous example, part A, we had the e to the negative 0.15x. And that required substitution. So I might be suspicious that this would require substitution because I have an e to the negative x. Well, because the x is there in front of the e to the x, it doesn't work. Had this been e to the negative x squared, we'd be great, but it's not. So in this particular instance, that x in front is, I like to say, it's kind of in the way. If it weren't there, I'd be ready to take the antiderivative. But it's in the way. So we need to get it out of the way, and the method of integration that does that is integration by parts. Integration by parts will let u be the thing that's in the way, which in our case is x. du is going to be everything else, e to the negative x dx. When I do the derivative, I get du is dx. Okay, now we have to be a little bit careful. In example A, we ended up, if you look back at it, we ended up dividing by 1 over 0.15, the negative 1 over 0.15. That 0.15 that came from the denominator was really the derivative of the exponent here. So we would, if we want to say this should be u equals e to the negative x, but if I take the derivative of e to the negative x, I have an extra factor of negative 1 because of the chain rule, so I need to compensate for that by having a negative out front. In part A, we had a negative 1 over 0.15, which compensated for the negative 0.15 in front of the x there. So we'll do this. Whoops, that says I have all my letters messed up here. This should say dv, and this should say v. Forgive me for that, please. So u times v minus the integral of v times du. So it says the limit as b goes to infinity, u times v is going to be negative x e to the negative x we're going to go from the natural log of 4 to b. And then we're going to subtract v times du. Well, v has a negative in it, and I'm subtracting, so that's really going to be a plus the integral from the natural log of 4 to b e to the negative x dx. All right, so let's go ahead and make the substitutions here of our lower and upper limits. Then we'll evaluate this limit here. So we've got the limit as b goes to infinity. Let's see, when x is equal to b, we get negative b e to the negative b. And then we let x be natural log of 4, and we'll get, well, we're going to subtract negative, so it'll be plus natural log of 4 e to the negative natural log of 4. And that's just the very first piece here there. And now we need to evaluate the integral. Evaluating that second integral, we'll have, once again, the antiderivative of e to the negative x is not simply e to the negative x, but negative e to the negative x. And we want to evaluate that also from the natural log of 4 to b. Now I'm going to hold off on taking the limit, but I am going to do one little manipulation. I'm going to acknowledge the negative b in the exponent of e will be the same as e to the 1 over b. So I'm going to write this as the limit as b goes to infinity of the opposite of b over e to the b. And then I'm going to do kind of the same thing with the second term there. We'll do the natural log. I said I was going to do the same thing. I didn't. The natural log of 4 divided by e to the natural log of 4. And now we have to substitute b and the natural log of 4 in for this second thing. We've got to be careful again that when x is b, we'll get negative e to the negative b. But then when x is the natural log of 4, we're supposed to be subtracting. So let's just put parentheses there to be safe, minus e to the negative natural log of 4. So here comes the tricky part. We have to recall something from Calculus 1. Here we have negative b over e to the b. B is going to infinity. Well, that means the numerator, ignoring the minus sign, is going to infinity. The denominator is also going to infinity. So we call this, for L'Hopital's rule, an infinity over infinity indeterminate form. So what we can do is we can replace the numerator by the limit as b goes to infinity of the derivative of that number, that value with respect to b. Go back to black here. So we've got the limit as b goes to infinity. We're going to take the derivative with respect to b of the opposite of b divided by the derivative with respect to b of e to the b. Natural log of 4 divided by e to the natural log of 4 is just going to be the natural log of 4 divided by 4. The exponential function and the log function are inverses of each other. I will distribute the negative to both terms back here, and then we'll rewrite e to the negative b as 1 over e to the b. So minus 1 over e to the b, and then we'll do something similar there. This will become a plus 1 over e to the natural log of 4. And we're almost done, believe it or not. Well, we've got the limit as b goes to infinity. I'm actually only going to leave a little bit with the limit here. The numerator, we get the derivative of negative b is just negative 1. The derivative of e to the b is e to the b. That's really the only place I'm going to have that limit anymore, because the natural log of 4 over 4 remains the natural log of 4. I'll just write it as 1/4 the natural log of 4. And then we have minus, we're going to let b go to infinity. If b goes to infinity, e to the b goes to infinity. 1 over a very, very large number is almost 0, so that third term is going to go to 0. And then the last term will be 1/4, e to the natural log of 4 being 1/4. E to the 1 over e to the b, this will go to 0, just like the other one did, because the denominator is getting very, very large, while the numerator remains small. And so our final answer, we're there, is 1/4 the natural log of 4 plus 1/4. Our next two examples are examples of the type 2 improper integral. If you look at these and inspect them, they don't feel like there's anything wrong with them. But let's look at the very first one. If x is equal to 1, we'll have 1 minus 1 in the denominator, which would be 0. We have a problem. So what we'll do is, in this particular case, we're going to look at the limit as, I'll say, a approaches 1. I'm going to put a direction on that in just a moment, but we'll just say this is the integral from a to 2 dx. Well, let's not even do that. Let's get ourselves prepared. We're going to write this as x minus 1 to the negative 1/3 power. All right, I said a moment ago that I'm going to put a direction on a. What do I mean by that? Well, we're looking at the interval from 1 to 2. From 1 to 2. A is a value that's close to 1, but it is approaching 1 from the right-hand side. So we'll put a little plus there. It won't make much of a difference in the end, but we should do it just for conceptual reasons. Okay. Now this one we could use a substitution. We would let u be x minus 1, du and dx would be the same thing, speaking of dx's. Or we could use just some logic to kind of convince ourselves that we got the right answer. So I'm going to, once again, let a approach 1 from the right. I take the antiderivative. If you have something to the negative 1/3 power, the new exponent will be the 2/3 power when we add 1. In order to compensate that, we would divide by 2/3, which is the same as multiplying by 3/2. Now, I might not be right because the inside is not simply just x, but it is x minus 1, and the derivative of x minus 1 is just 1. So when I check my work by taking the derivative of this, I'll see that it's not, I will get the actual answer. There's the chain rule just pops out an extra factor of 1. We want to evaluate this from a up to 2. So let's put 2 in for this. If we put in 2, we'll get the limit as a approaches 1 from the right. We'll have 3/2 of 2 minus 1 to the 2/3. And then when I put in a, it's simply 3/2 of a minus 1 to the 2/3 power. If we let a approach 1, that first term, well, there is no a in it, so it's just going to be 3/2 times 1 to the 2/3, or just 3/2. And the second term, if a is approaching 1 from the right, we'll have a number that's just a bit larger than 0. But some number larger than 0, but close to 0, to the 2/3 power is really just 0. And so our final answer is 3/2. We have a type 2 improper integral that converges, and it converges to 3/2. Be careful you don't say it converges at 3/2. At is usually referring to an x value. These are limits in a sense. Well, these aren't even limits. These are integrals, and so we're not saying x is equal to something. It converges to 3/2. Okay, so that was kind of a nice simple example. Our next one, we have to figure out why it is an improper integral. If x is equal to 1, we have 16 minus 1 squared in the denominator, which is just 15. That's perfectly fine. But in the numerator, we have 4, for the upper limit, we would have 4. 16 minus 4 squared will be 0. So that's the issue. So what we'll do here is we will let b approach 4 from the left, integral from 1 to b of dx over 16 minus x squared. Okay, so as before, we had another rational function. And when we had that rational function, I said, hey, just to be safe, let's see if substitution would work. If you look at 16 minus x squared, the derivative is negative 2x. There is no x in the numerator to compensate for that derivative. And so this one is a candidate for partial fractions. I'm actually going to do the work above. Well, I can do it off to the side here. I think I have enough room to do it off to the side. So it's really just 1 over 16 minus x squared, which factors as what? 1 over 4 minus x times 4 plus x. Be careful because the 16 is the first term there. It's got to be 4 minus x rather than x minus 4. Each of those is a linear factor. 4 minus x is linear, as is 4 plus x. So the numerators could be at most a constant. They cannot be linear. When you multiply both sides by the common denominator of 4 minus x times 4 plus x, we'll get 1 equals a times x, 4 plus x plus b times 4 minus x. If you remember from the partial fractions section, we would choose particular values of x to eliminate variables. So I'm going to let x be equal to negative 4 to eliminate the first one. If I get that, I'll get 1 is equal to, well, the first term will be 0. 4 minus 4 will be 0. The second term will be b times 4 minus negative 4, which is really 8. 8b. And so we find out that b is 1/8. Similarly, if we let x be equal to 4, then let's see. Well, the 4 minus 4 in that second term over here, the 4 minus 4 would be 0. And so we'll just end up with 1 equals a times 4 plus 4. So 8a is equal to 1, which means that a is also 1/8. Kind of a nice little coincidence there. Or maybe not. Maybe it's not a coincidence. I don't know. So here we go. The limit as b approaches 4 from the left. Okay, the integral of 1 from 1 to b of, okay, a was over 4 minus x, and that was 1/8. I'm just going to put the 1/8 out in front. 1 over 4 minus x. Plus b, that's also 1/8, divided by 4 plus x dx. Each of these is going to be a logarithm. I'm going to do the second one first here. I'll leave some space for the first one. I've got the limit as b approaches 4 from the left. Okay, the second one will be 1/8. It feels like it should be the natural log of the absolute value of 4 plus x. Now I want to check that. If I take the derivative of the natural log of 4 plus x, it's 1 over 4 plus x times the derivative of 4 plus x, which is 1. So the extra factor of 1 from the chain rule does not affect things. However, in the other one, I'm going to leave a little space here. It's 1/8. I think it should be the natural log of 4 minus x. It's going to be plus in there. When I take the derivative of this guy, however, it would be 1 over 4 minus x times negative 1. Well, we need to compensate for that negative 1 by multiplying by a negative out front. This is the integral from 1 to b. And now we can let b approach 4 from the left. Well, we've got to substitute things in, don't we? So this is going to be the limit as b approaches 4 from the left, negative 1/8, natural log, absolute value of 4 minus b, plus 1/8 of the natural log of the absolute value of 4 plus b. And then we're going to subtract. Minus negative 1/8, natural log, absolute value of 4 minus 1, plus 1/8, the natural log of the absolute value of 4 plus 1. Okay, so I'm going to look for my b's because those are where I could end up with some troubles. So I've got b in here, and I apologize, it's a little bit messy. 4 plus b. If b is close to 4, 4 plus b is going to be close to 8. The natural log of 8 is a perfectly fine number. If b is close to 4, 4 minus 4, would be 0. The natural log of 0 is undefined, so we have to investigate its behavior. Now let's think about this. We're approaching 4 from the left, so it's a number that's just a little bit smaller than 4. So this is the natural log of a small positive number. The natural log of a small positive number. So let me go over here, and in red we'll graph the function y equals the natural log of x. I know it crosses at x equals 1. The natural log of 1 is 0. Looks something like that way. And here's the trouble. If you have a small positive number, let's say right in this region, the y value is going to be a larger and larger negative number the closer we get to 0. So what that means is this part right here is going to approach negative infinity. I can see that from the graph because it's plummeting as we get close to the x-axis. Well, you have a negative 1/8 out in front. You're multiplying it by a ginormous negative number, and so this is going to approach infinity, so we say that this guy diverges. That's one that diverges. Okay, so there are several examples of improper integrals, both type 1 and type 2. The last little bit here, we're going to talk about something called the comparison theorem, which is a way to say, hey, I know it converges or I know it diverges, but I don't know to what. Oh, I forgot we have one more of these. Forgive me. We've got the integral from 0 to 1 of the natural log of x dx. Now, I gotta find the antiderivative of this guy. Let's see. Natural log of x. Derivative is 1 over x, but I don't know its antiderivative. But I remember that when I have a natural logarithm, what I first do is I look to see if its derivative is in the integral anywhere. 1 over x does not appear. And so the only method that I'm aware of to deal with natural logarithms is to use integration by parts. Now for integration by parts, we pick a u and we pick a dv. U is something we differentiate, dv is something we integrate. Well, if I knew how to integrate the natural log, I wouldn't be in this pickle, so u is going to be the natural log of x. dv, on the other hand, is going to be everything else, which is dx. du is 1 over x dx. v is simply x. The antiderivative of dx is like the antiderivative of 1, which is just x. Now, I jumped the gun here. I'm not even sure why I'm saying this is an improper integral, but if we look back at our last graph, just think about that last graph, the natural log of a number that's really close to 0 is going to be a really big negative number. So we've got the limit as a approaches 0 from the right of the integral from a to 1 natural log of x dx. All right, so we've got the limit as a approaches 0 from the right. Okay, we're going to use integration by parts. So it's u times v, x natural log of x, minus we want to evaluate that from a to 1, minus the integral from a to 1 of, okay, so this is always fun. V times du. Notice that when you combine these two, we've got 1 over x times x. 1 over x times x is just 1, so it's dx. Students often forget that they have to combine those things, and they don't know what to do at that point. Unfortunately, they often choose to evaluate each part individually, each factor individually, which is incorrect. Okay, so let's do the first guy, x natural log of x. Well, let's see here. This is the limit as a approaches 0 from the right. When x is equal to 1, we get 1 times the natural log of 1. We just discussed it. That's 0 minus 1, or a, times the natural log of a. And now we're going to evaluate the integral of dx. we need a function whose derivative is just 1, and that would be x, evaluated from a to 1. Okay, now we've got some wonderful things taking place here. The natural log of 1 is 0. Okay, well, that's the only nice thing that we really have taking place here. Okay, so this one, a is approaching 0. The natural log of a, on the other hand, is approaching negative infinity as a approaches 0 from the right. If you can't remember it, just look back at part E, we discussed that there. So this is what we called a 0 times infinity indeterminate form when we were talking about L'Hopital's rule. When you have a 0 times infinity indeterminate form, you have to turn it into a 0 over 0 or infinity over infinity indeterminate form. So we're going to turn it into essentially an infinity over infinity indeterminate form. The way you do that is you take one of your factors, either a or the natural log of a, you take its reciprocal and move it to the denominator. So here we go, and I'll explain what I'm doing here. I've got the limit as a approaches 0 from the right. I have the factors of a and the natural log of a. The prettier looking reciprocal is the reciprocal of a, and so I'm going to put that in the denominator. We'll check to make sure this makes sense. The natural log of a divided by 1 over a. Does this make sense? Well, when you divide by a fraction, you multiply by its reciprocal. If I divide by 1 over a, I multiply by the reciprocal, which is a over 1, which gets us back to the original. And then here we'll evaluate the x at both at 1 and at a. Okay, so I'm going to annotate here what I'm doing. For the first one, I'm using L'Hopital's rule. We'll use that in a moment. And here, I'm just going to evaluate the limit. So in using L'Hopital's rule, I can replace the numerator by its derivative. The derivative of the natural log of a is 1 over a. And I'm going to take the derivative of the denominator. That's a to the negative 1, which would be negative a to the negative 2. So that limit we're going to kind of deal with all on our own. When a is 0, 1 minus a just becomes 1. Okay, so let's see what's going on here. Now, something is amiss. Or maybe it isn't. That's okay. We'll figure this out in a moment. Okay, the a to the negative 2 that's in the denominator is the same as 1 over a squared. Let me write that. So I'm just going to do a little bit of jotting stuff over here. 1 over a divided by, okay, let's pull the negative out front. We don't care about that. 1 over a squared. Remember before we said when we're dividing by a fraction, it's like multiplying by its reciprocal. So we're going to look at the limit as a approaches 0 from the right of, we've got the negative, 1 over a multiplied by a squared over 1, and then minus this 1. Hey, look at that. A squared divided by a, the a's will cancel, or at least one factor of a will cancel in each, and so we're left with a, or the opposite of a actually, really. Negative a, as a approaches 0, this is just going to be 0 minus 1, which is negative 1. Wait a minute, negative 1. Okay, I learned before that when we got a number, we said it converged. So this guy converges, but how does it converge to a negative number? Well, if you think about the natural logs graph, it looks something like this. So we go here. The integral from 0 to 1 is a region that's below the x-axis, hence the negative 1. The rest of this video will be in a part 2 of improper integrals.